Processing and Food Engineering, Punjab Agriculture University, Ludhiana, Punjab, India. So today's my topic is design, fabrication and evaluation of pulse electric field lab scale setup for quality treatment of milk. It's not working. Okay. We have designed two objectives for this study. The first one was develop a lab scale pulsed electric field applicator for milk. And second one was study the effect of pulse electric field on raw milk quality and the shelf life. So coming to the objective one, to develop a lab scale pulse electric field applicator. So what happened, this is a technology which is coming under the non-thermal technologies. That means we have to treat whatever it is, juice, milk, food, etc., anything under the room temperature, and the food whatever will come will have the same quality as the heat treated food. So in India, there is no such setup available, and whatever setups are there, those are like abroad based, maybe Germany based, Netherlands based, and little highly sophisticated, and demands a very huge space, because this setup involves involvement of 50,000 voltage and 70,000 voltage, which is more than the lighting voltage in the sky. So for that, a separate room, a separate control system, everything is required. And so what we thought, why not to make a applicator which is smaller in the size, user friendly in the size, and at the same time can be applied to various food products, either it is milk, juice. So we have did trials on many food products. Today I'm talking about the milk. So we have decided the range. So normally the range starts from the 10 kilovolt up to 70 kilovolts. So according to Indian conditions, because in India the microbial content is little bit higher side in the milk as compared to the milk which is having contamination. So we have decided the starting voltage is a 25 kilowatt, and we have designed our equipment up to 60 kilowatt. So we have decided the shape as a square wave. So just imagine exponential wave. So in the exponential wave, what is happening? The highest peak, suppose 60 kV, in the exponential, it will go up to 60 kilovolt and it will stay there for microsecond and fall down immediately. In the square wave, it will go up and it will stay for a longer time like a square, and it will come down. So we have chosen the square wave, and that to the bipolar. It is little tricky to generate the bipolar waves because the circuits demands 8 generation material, and we have decided the duration as a 1 microsecond up to 1000 microsecond, because we were not sure whether our milk will be sufficient up to 20 microsecond or 300 microsecond. The system available are up to 500 microseconds only as such, and we have decided the pulse frequency also as from 5 to 100 hertz. So with these parameters which we have decided, so we have to choose the major components, which is first, number one is a transformer, because we have to produce 50 to 60,000 voltage. So transformer is the heart of our unit. Then the pulse generating circuit, treatment chamber, control panel, and oscilloscope. Apart from that, so when we started, so first we have prepared a small circuit to check whether we will be able to produce the square wave or not in India with this circuit. So we have prepared one little simulator of 10 kilowatt, and we were successful to produce the square wave. You can see also the square waves are produced. This is the small yellow device, is the oscilloscope. Then when we achieved the success there, so we have designed. So in that we were having the power supply from the AC current, alternating current, we have converted back into the DC current, and then the shifting the MOSFET power switching system. To the MOSFET power switching systems, we are controlling all the inputs from the control panel. From there, it will give the signal to the MOSFET driving system, and from the MOSFET driving system, again the signal will go to the power switching system that will switch when to generate the pulse and when to not, and then it will go to the transformer. From the transformer, it will come to the treatment chamber. So you can see this is my chamber. In that, it is a cylindrical. The first is the last one is the insulation. The before that is the cathode. Bottom you can see. Inside is again a cylinder which is anode, and between the insulation and the anode there is a container. Okay. So stage wise, I just described from the previous slide. So we are converting 230 voltage up to 60 kV voltage. This is just I can say the flow diagram. Then these are the specification of our transformer, like primary winding and secondary windings are there. So in the primary winding, there are only 230 windings, but in the secondary windings, there are up to 60,000 volt. To produce the 60,000, there are turns are 49,565 in 12 parts. So at each part, we can give the voltage of 10 kilowatts. So like that, we have designed the transformer. And we have calculated a number of capacitor, electrical potential, and whatever energy density we need to generate this much of power. And to hold the systems, we have calculated all the components, and with that number of registers, whatever energy is required. So we came up with this circuit. So you can see this is the complete circuits where each part from 1 to 5 have their own specific role. One is giving the variables, one is controlling, one is giving the one is generating the square wave, one is controlling each and every section. So number 5 is a micro controller. This controller is giving signal to every component. So from there we can see we have designed analog digital converter where the AC is converting into the DC. Then the MOSFET channel, it is very important because there are number of components are available which converts the AC into the DC, and then converting the pulse into the square wave. So we have used the MOSFET N channel to convert our wave into the square wave. Then when suddenly we convert the wave into the square wave, because it is a 60,000 voltage, sometimes circuit burns. So to avoid to see it should not burn, so we have provided more number of MOSFETs. So you can see the black one, the one, the total number of MOSFETs are 6. So like that, when we generate current and the voltage is very high, there is a limitation that with that there might be production of heat. That is obvious. So we should have a current limiting circuit also, so that there should not be any kind of burning. There should not be any temperature increment during the process. Otherwise, the food will, the temperature of food will rise and it will affect the quality. We need to treat our food at room temperature only. So we have regulators to regulate all the input voltage. Then this is the AT Mega 16 microcontroller from which we are controlling our whole circuit. So you can see there are number of 21 pins are there. So how it is connected with the variable, how it is connected with the MOSFET, like that. So I'm not going much into the details because I have seen that number of participants are having the scholars are from different backgrounds, so they might not understand in detail the electrical circuit. So microprocessor, this is the details of microprocessor. Like we have 2 pins for power, 2 pins for oscillator, 1 for the resetting, 1 for the AC/DC circuit, like that, 1 for the LCD display. So this is T mega circuit, which I have discussed earlier, will control the circuit. This is the complete circuit. Then we have to program also, like we have 1000 microseconds. So at each microseconds, we have programmed all the circuits so that at 1 microsecond also we can have all the variables, we can have all the voltage, we can have all the time duration, we can have all the frequencies, and at the 100 microsecond also we should have. So for 1000 times we have run the programs, and for each microseconds we have set everything. So this is just a screenshot of what assembly language, a program we have used. So here's the clear-cut diagram. So you can see one is the cathode. In the cathode, the little dice inside is acting as a cathode. It is an electrode. The first top cylinder is acting as an anode. The in between the cathode and anode, we have the container. So these are stainless steel, and the insulator is wood only. So very raw kind of container we have, but we were successful to run the milk inside it. So these are some dimensions of my setup. So the total capacity was 240 ml. That is much more compared to whatever commercially setups are available. For a lab scale, the maximum capacity is 50 ml. So we were able to increase the capacity, and we can actually increase capacity with this kind of model. We can go up to 1 liter also. It is a huge success. So you can see the filling of milk inside, like now the whole milk is in contact with the container, and both the cathode and anode, and the gap should not exceed 1 centimeter. So this is the limitation, because if we increase this gap like more than 1 centimeter, then apart 60 voltage must be 120 voltage. So the voltage will get double. So we have to have that electrical density between to the food products. The gap between should not exceed 1 centimeter. So this is the calibration we have done. You can see the square waves were produced. This is a control panel from where we can control treatment time, pulse time, frequency, like that. And you can see we have set 900 microsecond, 90 hertz for 5 seconds. So from here and below is the regulator for the voltage. So from here we are giving input to our treatment chamber. So this is the whole PEF applicator. So you can just see, even you can Google also. If you can, we cannot find any system like this, a very small. This the device is very small, and this device was able to produce 70,000 of voltage. Even you can see the big transformer, roadside transformers are able to produce for 50,000 of voltage. So this is like 20% part of that big transformer. From that, we were able to produce this much of voltage, and also for a more time, like up to 100 microsecond. So to make this we have used almost like these are the components, like how many capacitor we have used, almost 29 capacitor, diodes, and MOSFETs, registers, like that, variables, transistors. So these are some components which we have applied for manufacturing of this circuit. Now the second part was excuse me, to study the effect of pulse electric field on the raw milk quality and shelf life. This is the important one. So what we have done the preliminary trials. We have started from the 25 kilo voltage for the 5 second, and up to the 90 hertz and 40 second and 60 kilowatt. From that, we have concluded that the higher the voltage, higher the time, higher the frequency, and higher the pulse width, is resulting into the higher the destruction of microbial content in the milk. So what we have said, we have selected parameters 90 hertz and 900 microsecond. From here, we have fixed these two parameters and we have done the variation in the voltage and time. So with that, we have run programs, and we have taken the milk at 25 voltage for 5 minutes and 40 voltage for 20 minutes, but the frequency and pulse width were fixed. So like that, we have fixed the pulse width and pulse frequency, and we varied only the voltage and treatment time. From there, we have treated the milk, and then we have divided the milk, like raw milk was stored at ambient temperature, raw milk was stored at refrigerated, then PEF also stored, but one sample was at ambient, one sample was at refrigerated, and there was a double pass also. Double pass means we have given the treatment, suppose for 10 minutes, then again we have given the same milk again for the 10 minutes, because in India, the microbial content is not like 300 colony forming unit in 1 ml. It is up to 40 lakhs per ml. So this is huge. To reduce that with a very mild treatment is difficult. So we have to increase the voltage and time, and we have to double pass it. But there was no effect on the quality. So what we have seen, the milk from the 42 lakh CFU per ml, this the normal condition of milk in India, we were able to reduce it with the single pass to the 1,23,000 in India. That is up to 70% reduction, and we were able to keep milk safe for 11 hours at room temperature. So it is like the milk from the when it milked, like suppose 4 a.m. in the morning, so after 11 hours, like 3 p.m. in the afternoon, so till then the milk was safe. That means without any refrigeration, without any other processing, we can actually transport milk from one location to other location, and it was safe. So our study concluded that we actually might replace the little bit of refrigeration cost in India, and can just treat the milk with the PF and can transport to the processing unit. So during there are many other parts also. We have prepared the products also, but today I'm just concluding here. So with this, I'm concluding my presentations. Thank you.